Okay, I will start from the end effect. I mentioned the end effect a little bit yesterday. As I tell you, if you apply a load to the rock specimen here, then it seems the rock will shorten. And because of the Poisson's effect, the rock will expand. If the rocks expand, so you apply a load like this, and you will have a shear stress along the end of the specimen, at the boundary of the specimen. So this will be the so-called end effect. This end effect will become stronger if you have a shorter specimen. If you have a longer specimen, then the influence of the end bearing will become smaller. So the size of the shape of the specimen will influence the testing results. This figure shows you if we have a different sample size, sample shape from the very long sample, like the length divided by diameter equals to 3. It means if this is 3, then the diameter will be 1. Okay, understand? This will be the testing results. If you decrease the ratio, it means you make the sample shorter and shorter. Then you will have the testing results from this to this, to this, to this, to this, and to this, for the height divided by d equals to 0.25. It means if you have the diameter equals to 1, then your sample height will be 0.25. Okay? So it is very significant influence by the sample size, and the reason will be the end effect. If we try to eliminate the end effect using the so-called Bush plate, so we will have a lot of needles. So if we apply the load with a lot of needles, can you understand? And apply load. Then if very stiff needle, so when you apply load, then it will be like this. The load will be applied like this. Not like this, but like this. Then if you have a sample expansion, then the needle can freely change the shape. So you will not really have the friction. Okay? That is, if you use the Bush plate, then you will not really have the end effect. The end effect can be eliminated. Under this condition, no matter which kind of sample size, you will have identical stress strain curves. Okay, so the end effect could be quite important. I already explained this to you. Sorry, it's the brush platen. Also, using the brush platen will be the end effect can be eliminated. However, this kind of loading equipment will be difficult to use, so it is not suggested by the ISRM standard. For the ISRM standard, they highly recommended to use the polishing. You need to polish the surface of the specimen. And the standard says they do not suggest to use the lubricating materials. Do not suggest. Because this will induce another kind of problem. So it is not recommended to use those way to reduce the friction. So the standard says they will only accept the polishing using mechanical way to polishing the sample. So that will be the only way to treat the sample to minimize the so-called end effect. Okay, so I already explained this to you. So the end effect cannot trying to use the lubricated or soft material between the specimen and the platen. So only the machine way will be the only recommended way to minimize the end effect. And as I said to you, you will have the concave upward. This will related to the micro fracture closing, but this also related to the specimen preparation too. So according to the standard, they suggest if you have a sample to be tested, they should be very flat, the first, and two ends should be parallel. So that will be very important points in the standard. Here shows you the allowable precision for the preparedness of your sample. The flatness of the sample should be within 0.02 millimeter. It will be 20 micron. And the plane deviate from the sample axis cannot exceed 0.05. So there are two things. The first thing is these two plane sample end should be as smooth as possible. This will be one thing. The other thing, they need to parallel to each other, and they cannot be like this. They need to perpendicular to the sample axis. So the allowable precision will be here. Understand? 了解吗？没有太大的反应，这样子我会很害怕啊。应该是很容易了解了哈。Okay, even we trying to use the spherical six. What is a spherical six? Sometimes to keep the loading in have a very good alignment through the axis of the sample, we were trying to use spherical six. The spherical six will this will be the spherical six. If you apply a load, then this assembly can keep the loading in a very good vertical directions. Have a very good alignment with the sample. So the sample will be like this. To avoid the 怎么讲呢？就是要避免它会有偏心，不要让它有偏心的载重。Okay, so this will be kind of a design called the spherical six. Even you use this, if the end of the specimen did not really parallel, or it's not really perpendicular to the axis, this will be the axis of the sample. If this and this is not perfectly perpendicular, then even you use this, you still have a significant influence on your stress-strain curve and on the strength. So it will be quite sensitive. For research purpose, it is suggested to have a higher precisions if you focus on the rod test research. Okay, this I already mentioned to you yesterday or several weeks ago. This will be the inference of the specimen volume. The larger the specimen volume is, the smaller the strength will be. A lot of theory to explain this kind of phenomenon, but most of the statement or the explanation for the flow weak point or some flow within the sample will be a very good explanation. If you have a larger sample, then you will have the opportunity to have a more flow effects of the sample to initiate the failure of the sample. So we tend to use a sample in a reasonable size. And the other important things you need to always remember, if we want to eliminate the so-called scale effect, we hope we can contain as much grain as possible for a rock test. For soil test, you have a sample in this size. If you have a sample in this size, there are thousands or millions grain particles within the sample, so you will not really have the scale effect. For rock, the grain could be larger, but the sample size should at least 10 times larger than the sample grain, the grain of the rock sample. Understand? For sandstone, you could have a lot of grain as well, and you will have some cementation within the voids. The sample diameter here should be 10 times larger than the diameter of the grain. Okay, to eliminate the scale effect. So this will be a standard to use. The 5 centimeter or 50 millimeter will be the standard diameter of the rock test in laboratory. I already explained this. So the size effect of the specimen volume could be explained by the distribution of flows within the materials. If you have a larger volume, then you will have more flows. Then this will reduce the strength of the materials. And then it will be the influence of the strain rate on the stress strain curves. So we are talking about the many influence factors on the stress strain curve of rocks. The strain rate will influence the stress strain curve, but it could not be so significant within certain range. Okay, so the ISRM Commission recommended a loading rate like this. I already showed you yesterday. This means a typical rock will fail within 5 minutes to 10 minutes if you apply a loading rate like this. Okay. Some people suggest to consider the loading rate in terms of the strain rate. It will be the strain control, but not the load control. They consider the loading rate from the strain rate, actual strain rate, rather than use the actual stress rate, like I showed you, 0.5 to 1 MPa per second. Using strain rate, the strain rate could roughly around this order. Every second, the strain rate will be -5 to -4. Because we talk about the strain rate, you know, the strain is the no units for strain, because the strain will be length divided by length, so you will not really have units. So -5 means 0.01% strain. 0.01% to 0.1%. It will be 0.01%. 0.001 to 0.01% strain rate. Under this condition, the strength, the stress strain curve and the strength will not influence too much by this strain rate range. Even we expand to this strain rate, the influence will not too significant. The influence could be the uniaxial compression strength grows up twice than the slow one. So usually if you have a faster loading rate, then you will have a stronger results you derive. There will be the influence of the strain rate. But within this range, it will be okay, not influence too much. Okay? Then, I like to describe another important point to you. This will be the stiffness of the testing machine. This will be a picture of a loading frame in our institute. This loading frame, you can see, if you have a specimen here, then you have a hydraulic jam here. So you will pump oil to the hydraulic jam, and this will elevate it. This part will elevate it. And you have a specimen here. When it elevated, keeping rising up. Finally, the rock top surface will touch this part. Then the rock will subject a load. Correct? How the load be subjected? Actually, it will be come from this frame. We call it a loading frame. If you have a very strong loading frame, then the rock move up and touch here, even though you still pump the oil into the hydraulic pumps, oil pumps. The frame will inhibit it move upward. Can you understand? There will be the stiffness of the loading frame. There are a lot of, not a lot, there are some testing machines with very stiff loading frame, like the one in civil engineering department. You have the MTS system, and the MTS system you will have a 4 steel wall, but not 4 column. 这个是牵涉到就是机器的进度。那这个是在我们实验室的这个延时荷重机，它是4个柱子4个柱子。那你油压往上推，它就是那个延时室里就会往上跑，碰到上面它就会顶住了，上面放一个 load cell， 所以它往上推的时候碰到那个 load cell 就可以量它的这个受到的这个力啊。那它为什么没有持续在往上推呢？因为这个 loading frame 荷重的这个行架不允许它往上跑嘛。你没有这个行架，你油压先进，你往上推，它就一直往上跑，一直往上跑。OK。For the 那个土木系的那个 MTS 的系统，它就是4堵钢墙，不是4根柱子，那个的 stiffness 就会比我们实验室的这个 loading frame 这个 stiffness 要高很多啊。Why the stiffness of the machine matter? This will be related to the testing results to get the complete stress strain curves. You have a stress strain curves like this. If you have a stiff machine, then you have the opportunity to get the complete stress strain curve like this. However, if you have a soft machine, the stiffness of the loading frame is not strong enough, then what happens? If you load the rock using the machine with not enough stiffness, then the stress strain curve will goes up to here, to here, to here, and the rock will explode suddenly because of a brittle failure. It will be failure suddenly. So you cannot get the complete stress strain curve. If you use the stiff machine, then you have the opportunity to get the complete stress strain curve. I will not talk too much about the importance of the complete stress strain curves. I can tell you, sometimes we were trying to use the stress strain curves to study the creep effect or the fatigue. You know fatigue. If you load a material cycling for a long time, the material could fail. We call it fatigue. 我们讲有一种叫做金属疲劳，就是你如果要是反复荷重，你可能会让它的这个强度就是材料会提早损坏，那个叫做 fatigue. Some engineering applications you need to well use the complete stress strain curve. I'm not pretty sure if I have enough time because I have to left at 30. I will try 5 minutes left. The specimen will be here, and you will load the specimen. Then this will be the stiffness of the machine. If we assume the stiffness of rock and the machine can be well represented by a spring, you imagine it is a spring. Then this will be the stiffness of the machine, and this will be the stiffness of the specimen. Okay, so that will be the displacement versus load, and the slope will be the stiffness of the rock and of the machine. We call it the K machine and the K system. Sorry. Yes, specimen. So the Ks will be the stiffness of specimen, and the Km will be the stiffness of machine. I was trying to explain a little bit to you why the stiffness matter. I will skip those description using the text. I will explain it directly to you. Please imagine if I have a very I don't really have a stiff machine. When I apply a load to the specimen, then the load will increase because of the increase of the displacement, actual displacement. When the actual displacement increase, then the load will increase, right? If you have this part, the displacement increase, the load increase. Displacement increase, load increase. Displacement increase, load increase. Displacement increase, load increase. To the peak stress, when the displacement increase, the load will start to decrease. Okay? If you have a complete stress strain curves like this, when you go beyond the peak strength, if you increase actual displacement, then the strength resistance of the specimen can be dropped from here to here. Okay? The stress can be subject by the specimen will drop. For example, from here, if this is 100 and it dropped to 90, the strength will drop from 100 to 90. Okay, for your machine, it will be the same thing. If the strength increase a little bit after the peak, If you have a very stiff machine, then you have a small displacement, then you will have a very large drop for the load because you have a stiff machine. So the slope will be very large in this part. If you have a stiff machine, that could be like this. The stiffness of the machine will be like this. So when the displacement make the rock stress drop from 100 to 90, then the machine have the capability to drop from 100 to 85. The rock can subject 90. The machine can drop to 85. So the rock will still survive there. Understand? If you have a soft machine, the rock will drop from 100 to 90. However, you have a very soft machine. You have a displacement. Then the stress can only drop from 100 to 95. Then the rock cannot subject this such high stress. Then the rock will fail suddenly. Can you understand this? So instead, if you don't really have the steam machine, how to make the test? It'll be you need to have some high technique. It'll be like this. If you load the displacement and it goes up to the peak, and you will unload a little bit using your hand, and load it again, and unload it very fast. Load it again, unload it very fast. Then you can have the complete straight strain curves. If you don't really have the stiff machine, can you imagine? If you can imagine, I don't really need the rest of the PowerPoint. I will stop here and take a short break now. This will be the soft and the stiff machine I explained to you. This will be the straight strain curves. This will be the straight strain curve. This will be the soft machine. This will be the stiff machine. For soft machine, when the rock subject the stress beyond the peak strength, then the strain curve will start to decline. For example, if you have a displacement delta S, then the strength the rock can subject will drop from PA to PB. However, your machine is soft machine. Under the same displacement, delta S, the machine can only drop the force for such an amount. It can only drop from PA to PF. Under this condition, the machine will still apply a force equals to PF on the displacement. As you know, the displacement can only subject the force equals to PB. It means the force applied by the machine larger than the force of the displacement can subject. Then the rock will fail suddenly. Understand? On the other hand, for this case, if you have a displacement equals to delta S, then the stress of the rocks goes beyond A and have this displacement. Then the force the rock can be subject will drop from PA to PB. Under this displacement, the machine can release a force in such a large amount So the force applied on the rock specimen will from PA to drop to PG. This force applied on the specimen will smaller than the load the rock can subject, lower than the strength. So the rock will not fail. Okay, so the idea will like this. If you have a soft machine like this, when the displacement goes, when the load goes from A and after displacement to drop to here, and you have a soft machine, you cannot release the force as much as we require. Then you will control, as I shows you, if you load the machine, if you load the machine in this direction, for example, if you have a motor, if you rotate it like this, when the rock just attain the peak strength, you will rolling back of the hydraulic of the loading system. If you rolling back, then the hydraulic system in the original, it will push downward. When it goes up to the peak strength, you make it go back. So you make it drop a little bit. And you load it again. And drop it a little bit. Load it again. So under this condition, even you have a soft machine, you have the opportunity to get the complete stress strain curves. If you have very good testing technique. Okay. I already explained this to you. This will be from the energy point of view, but the idea will be the same. Okay. So this, especially for the brittle rock, this will be very sensitive. If you want to have the complete stress strain curve, then you have to use the steam machine. Or another possibility is trying to control the machine in a smart way. So I already mentioned to you, you can control the machine by the experienced tester. This work can also be done by the so-called servo control. You know servo control? Servo control means the machine can doing things via the command from computer. Okay. The servo control, the very good example will be the airbag. Airbag will be kind of servo control. If you have a sudden hit, then the machine will inject the pressure to the airbag. Then the airbag will blow out to prevent you get hurt. So there will be some, according to the trigger, to decide the response. Okay. So you can imagine if the things I tell you, you can try to rolling back of the machine of the loading directions. When you find the rock already goes up to the peak stress. Okay? So you can make the judgment by your brain, and you can make the response by your hand. If you have a very good sensor to detect every single information, and you have some rules to ask the machine to doing something according to your idea, then it is possible to ask the machine doing the same thing like I show you. Like it? Loading, unloading, loading, unloading, and finally you can have the complete straight-line curves. How to make the servo control? The first, you need to sense the information or the response. You can try to use the load subject to the displacement, or you can try to use the displacement, including vertical displacement and the horizontal displacement, to detect the condition if the rock already goes up to the peak stress. You can calculate it. If your stress keeping increase, then you still not go to the peak stress, right? But if the load starts to decrease, then you can have some rule to ask the computer to tell the machine, okay, right now the stress already dropped. You need to lowering down the pressure to make the loading become slower and slower and slower. Okay? Then if you find the drop already stopped, or you don't really have any deformation, it means the rock is not really subject to the stress. Then you will start to ask. You can sense this, and the computer will tell the machine to increase the load again. So this will be kind of servo control. If you want to have the servo control, you need to have, if you want to control, you need to have the, from the computer, you need to change the digital information to analog information. Do you understand? All of the machine will be controlled by the analog signal. The computer will only have the digital information. So you need to have a convert system to convert the digital information to analog information. We call it the DA card. If you have a DA card, you can try to change the digital information into analog information. On the contrary, if you want to get the information from the rock testing response, you need to get the information from the sensor. Usually, sensor will get the analog information. So under this condition, you need to have AD card to convert analog information to digital information and transport into the computer. Then the computer can communicate with machine in double way. Okay, so this will be kind of way to get the complete straight-line curves to using the servo control system. Okay, I already explained this. To make the servo control, you still have a lot of way to design your servo control to get the complete straight-line curves. I will not focus too much on this aspect, so please read the PPT and read your textbook to get more information on these aspects. Okay, this will be the introduction of the rock testing, loading frame, and the testing system. I will not focus too much on this. Okay, you can read this to understand the whole system of the loading frame. Okay, this I already mentioned this to you. The servo control can can be done using different control variable. So it depends on which control variable you want to have. You can control via force and you can control via displacement. It depends on how familiar to the rocks you can. So if you understand the performance of the material, then you can make your surf control to get a very good testing results. Okay. So that'll be something we talk about. If you have the brittle material, or if your material will be strength softening, then it will be very hard for you to get the complete stress strain curves. Regarding to the application of the complete stress strain curves, you can read the textbook written by Goodman. There are 2 pages to talk about the application of complete stress strain curves. Because we talk a lot to say how to obtain the complete stress strain curve. And we introduce a lot about what is the stiff machine, right? But maybe you want to know why we need to have the complete stress strain curves. You can read this, only 2 pages. Okay, or maybe you can try to Google. It will be easy for you to get the material via web. I will not stop and I will continue. I will stop at 20:25. 9:25. Okay? So as I mentioned, you can control using axial displacement. And you can also control by the circumferential displacement. What is the circumferential displacement? I already introduced you a little bit. This will be the circumferential displacement. So measure the lateral displacement. We call it the circumferential displacement. Okay. This will be an example for kind of rocks. It will be the limestone. This will be the complete stress strain curves. So you can see here, in general, this kind of rocks will be brittle. If you don't really have a stiff machine, when you load it, you will have this kind of curves going up and concave to here. And when it drop down, if you only have the soft machine, it will be break immediately. So you cannot get this. How this was obtained? This will be like I tell you. You load it, and when it goes up to the peak strength, you unloaded it. And load it again, unload it, load it again, unload it. So you will have this, and going down, and going up, and going down, and going up. And here, going down, going up. So you will have the complete stress strain curves like this. This will be the complete stress strain curve. Okay? And this will be the relation between the axial strain and the lateral strain. Okay? You can find it will be loading, unloading, loading, unloading, loading, unloading. You will get this. So the control can be done by the lateral strain. Okay? Or the control can, you can use the axial strain to make the good control. Both ways will be okay. I will skip this to introduce you some measurement device. I will still focus on the stress strain relation. This shows you several stress strain curves of different rocks. Here you can find 2 groups. This will be one group here. This will be the same group with this. And this will be the same group. So this one, and this one will be the same group. This, and goes up to here and fell here. This, and this will be the same group. You can find for this group, it will be break suddenly, or even the stress strain curves will have a negative stiffness, like this. We call it a class 2. It means it will be more brittle. So this, and this will be class 2. It will be the brittle rocks, relatively brittle. For class 1, it will be this, and this. So you can see, you can make the difference between different rock behavior from the complete stress strain curves, and you can make the distinguish. Okay, and this will depends on the rock types. Different rocks will have a different behavior. This will be the 2 class. This will be the class 1, and this will be class 2. I already showed you. This will be the difference of the post-peak behavior. So when we talk about the complete stress strain curves, actually we are trying to talk about the post-peak behavior. Okay? So I might give you a question next week, such like, what is the post-peak behavior? Or what is the complete stress strain curves? And how to categorize the complete stress strain curves or the post-peak behavior if the rock is brittle, or if the rock is if your machine is not a stiff machine. How to control and get the complete stress strain curves. Or I could ask you, what is the so-called stiff machine? There will be the possibility to ask a question. What is stiff machine? Why we need to have the stiff machine for rock testing? For what? Why? What benefit from the stiff machine? The question like this. If you if you are keeping follow my talk, you can answer those questions easily. If you did not, please go back to see the material or read the textbook by yourself. Okay, from the above literature, talk about the brittle or relatively not so brittle, or the class 1 and the class 2. You will have the tensile fracture for the class 1. And for the class 2, the failure mode will differ from the class 1. For the class 2, you will have the shear fracture or faulting along a macro crack, Collinson by the micro cracks. So there will be the mechanism to have the different stress strain curves or different types. Okay, so the class 1 will be the local tensile fracture. This will be the local tensile fracture, and this will be the failure along some plane related to some shear fracture. Okay. For the class 1, you will have many vertical or many micro fractures parallel to the maximum principal stress or parallel to the axial directions. I already mentioned this to you yesterday. So you will have many fracture like this. If you have maximum principal stress in this direction, then you will have many vertical fractures. Okay, so this will be some mechanism for different types of the rock. It will also talk about the different classes of the rocks. So for some homogeneous fine-grained rocks, I already showed you the stress strain curves of the limestone. This will be the class 2 failure. Class 2 failure. The peak stress or the stress strain curves were mainly controlled by the slip along some macro fractures. So there will be the difference between two classes. Okay, so the class 2, this one, it will be homogeneous fine-grained rocks, like the some basalt will be kind of fine-grained rock, because they don't really have the time to crystallize. You know, basalt will be the very fast cooling process to have the basalt. So this will be the so-called fine-grained rocks. You will have the stress strain curves like this. So it will be related to the lithology. Okay. Somebody says, although we have the post-peak behavior of the rocks, it could not be the real material behavior. We have some theory to talk about the behavior for the post-peak. Somebody thinking about this will not be the true material properties. Okay, so you need to keep this in your mind. This will be also the case I showed you. I told to you, you can loading, unloading, loading, unloading, loading, unloading, and you can get this kind of testing results. This will be another rock specimen testing results for the post-peak behavior. Okay, I will skip all of this. From this, you can see some interesting phenomenon. For this, and this, you can find the slope will be different. So it means the stiffness will be different. So this will be stiffer and became softer. When the axial strain became larger and larger, the damage of the material will become more serious. So the fracture became more and more. So the stiffness will became gentle and gentle. And the other will be the irreversible strain. When you load it, unload it, then you will have the permanent displacement. So it will be irreversible strain or the plastic strain. Okay, so you will have the hydrostasis. I already mentioned this to you. The modules will decrease. Okay, so this will be the characteristics of rocks subject to loading and unloading. So this will be the influence factor on the rock mechanical behaviors. Okay, so after a briefly introduction of the different controlling factors on the rock mechanical behaviors, the follows will be the several testing methods for rock. This one, I already mentioned this during the class talking about the wall strength. I already mentioned this to you. I will go through it very fast. So this will be the point load index, which defined by the load make the rock split, broken, divided by the equivalent diameter square. So this will be the point load index. And the point load index should be transferred into a standard size equals to 50 millimeter. Because of the size effect, if you have a small rock specimen, then you will have a higher strength. If you have a larger size specimen, then you will have a smaller strength. So you need to make correction to make the results approach to the size equals to 50 millimeter. I already show you the curves. Right now here, give you an equation. You can calculate the equation. You can calculate the IS50, which is made the size effect correction using this equation. For example, if you have the diameter of your specimen equals to 50 millimeter, then the correction factor will be 1. Understand? You don't need to make the correction. If this larger than 50, then you will have a factor, correction factor larger than 1. If you have the diameter smaller than 50, then you will have a factor smaller than 1. Understand? So that will be the correction, corrected to the standard size. And the uniaxial compression strength will roughly equals to 24 times the corrected point load index. Okay? So the IS50 will be the corrected point load index. So I could give you a question in my examination. What is the point load test? How to get the uniaxial strength from the point load test? Okay? This will mainly talk about the equivalent diameter. The equivalent diameter, because when we try to use the point load test, usually it will be very convenient to make the measurement in the field. If you have outcrops and you have rock blocks, or if you have a tunnel excavation, then you will have the in situ blocks from the tunnel, fresh materials. Then you can get the rock specimen to doing the point load test directly. You don't need to cut the specimen and care about the ratio between height and the diameter and the size and the polishing is parallel to each other. A lot of things to consider, right? So last 1 hour, I introduced a lot of standard to measure the uniaxial compression strength of rocks. For the point load test, it will be very easy, very simple. You are not limited by the sample shape. You can use the any kind of shape to make the calculation. The only thing is, if you have an irregular shape, it's not circular. You don't really have the diameter. So you have to calculate the equivalent diameter. The equivalent diameter will be the area when the rock broken into 2 pieces. You will have the area. The area you imagine it will be a circle. So you can calculate the equivalent diameter. So that will be the way to make the calculation. This will be the correction curves I already show you, and I give you the equation already. Okay, so this will be the correction of the size effect. So this will be the correction factor I already showed you. I want to remind you an important point. Also, we trying to use the point load test to derive the uniaxial compression stress of rock, right? However, this kind of point load test, the rock is not really felt via compression force. The rock felt under tension stress, actually. Can you imagine? If you have a rock and you apply a point load on a rock, then it will be split into two pieces. Actually, it will be filled by the tension stress. I will show you another typical testing method to measure the tensile strength of rock. We call it the Brazilian test. We will try to use a disc and apply a point load on the disc. And the disc will broken into two pieces. Then we can measure the tensile strength of rock. I will show you later. The point load test will be the same. The point load test will make the rock fail by tensile strength. Then you could curious, how can we correlate the point load test results with the compression strength of rock, right? Because I told you it will be tensile strength, actually. The reason is we know the tension strength will have some correlation with the compression strength. If you have a higher strength of a rock, then you will have a higher compression strength of the rock, of that rock. Okay? So that will be the reason why we correlate the point load test results with uniaxial compression strength. Also, the rock is filled by tensile stress. Understand? 虽然我们的岩石在点荷重实验是因为张力破坏，可是我们却拿这个点荷重实验的试验结果去推估岩石的这个单压强度。原因就在于岩石的张力强度其实跟压力强度是有很好的关系，有正相关。那所以我们才有机会用一个是造成张力破坏的一个实验，然后去跟压力强度去建立关系。所以这个主要是这样子的一个概念。Yeah. If you trying to make the observation of the rock surface, the fracture surface, you can find a lot of pattern which shows the failure is induced by tension. You can find some features. So there are some textbook talk about the surface features to identify what kind of failure mode the material subject. So according to those pattern, we can understand it will be failed by tension stress. Okay? Sometimes this will be a typical features. If you make the observation of certain rocks, and you could find if you have a hammer and hit somewhere and make the rock broken, or you trying to put some nail into materials and make it split. Under this condition, you will frequently observe this kind of pattern or features. This will be the propagation of the failure. And this will be the stop line. So it propagates from here to here, to here, to here, to here. So this will be kind of a pattern for the surface. And you can make some judgment what kind of failure mode it could be. Okay? For very soft rocks, like the poorly cemented sedimentary rocks, or if you have very high anisotropy, like the slate or schist. So this kind of rock, you need to use the so-called point load test with caution. You need to carefully to use this. Okay? you will get a very high degree of scatter. So under this condition, you could do a lot of testing, because this kind of testing could be very simple and very quick. So you can do a lot, and to evaluate the scatter results and to make a good judgment, to use those to correlate with the uniaxial compression strengths. Okay, or you can also evaluate the anisotropy of the rocks. For example, if you have a slate formation and you can find a very clear foliation of the rocks, then you can make your test in different directions to measure the IS and to identify the anisotropy. So that could be, you could use this to evaluate the anisotropy. All of the testing methods I introduced to you can be focused on, can be found in this standard. Sorry.
You say the statement you put according to this point rock. So sometimes this homogeneous we can put anywhere. But if the heterogeneous we have some big grain size. If you put the stiffness there, then this may have a very strong and we cannot accept the group in this condition. How can we solve the problem? To find where you don't have that very big grain size.
You need very big grain size. You talk about slate or something.
The
Granite.
have the rock.
Quartz.
Yeah, it have sometimes big, and sometimes small. If it's a heterogeneous one, and if you put the point rock there, and sometimes you put at the crystal, it's not exactly the rock.
It is true. It is true. So you will have some scatter if you make the measurement, like you said. So the point of test is not really the best way to get the uniaxial compression strength. The best way will still be the standard uniaxial compression uniaxial compression test conducted in laboratory. That will be the best. But the test will be time consuming and it will be more expensive. But when you work in the field, if you have the point load test machine in the field, then it will be very easy or convenient for you to do a lot of tests. Okay? So the problem you have, we can thinking in another way. We still have the heterogeneity in the field, right? Even for granite, it's quite homogeneous. Somewhere you could have this type of granite, and at the other location you could have another type of granite. For the rock testing in laboratory, you could only have a limited sample. But if you're using the point load test, you can have a lot of sample. So you can well consider the variability of the material if you use this to estimate the uniaxial compression strength. So please, thank you. You remind me, this will be a strength index. We will not talk about this will be the strength parameter. This only be an index. So there still be the shortcoming within it. You already indicated one of them. So we should always remember there will be only kind of index. It's not really a true test. Okay, so please read this for when you need to doing some testing. You need to solely follow the standard, the specification to doing the test. Okay? This will be different shapes and how to make the calculation. I think you can read this by yourself. So I will skip this. And this is how to calculate the equivalent diameter. If you apply the load in this direction, then the fracture area will be a rectangular shape, but not circular. But you can calculate the equivalent diameter to make your calculation. You can read it by yourself, and I will not waste time on here. So this will be the example for an irregular shape rocks. So you can do in your test in this condition. There are some limitation for the testing. So you need to have a good shape to make the test. Okay. So the dimension, the ratio should not be too large or too small. This will be the inference of the anisotropy. I already mentioned this. So you can apply the test perpendicular to the weak plane or parallel to the weak plane. Okay. And then I'd like to introduce you the direct tensile strength test. So the tensile strength test, we will have 3 different types for the tensile strength test to get the tensile strength of rocks. Please notice this will be a very big difference between rock mechanics and soil mechanics. For soil mechanics, we don't really have the so-called tensile strength test. No tensile strength. For soil, tensile strength equals to 0. For rock mechanics, the tensile strength will be one parameter which could be useful for the engineering design. So the tensile strength test will have 2 different groups. The first group will be the direct tensile strength test, and the second group will be the indirect tensile strength test. The indirect tensile strength test, we will have 2 typical way to measure the tensile strength of rock. The first one will be the one I already mentioned to you. That will be the Brazilian test, and the other will be the bending test. So you can imagine if we bend a material, if you bend it, then you will have a compression stress here, and you will have a tension stress here. Okay? So we will try to use this idea to measure the tensile strength of rock, to make the rock bending. Okay? And the Brazilian test, we're using a disc, and you apply a load, concentrate load on the edge of the disc. Then you will have a tensile stress within the disc. I will show you the stress distribution within the sample, the disc. So I think I don't really have time to go through all of them. So I will stop here. And next week we will have examination. So the examination will cover all the material I teach you, from the initial notation to the stress analysis, to strain analysis, to stress-strain relation, to the discontinuities, characteristics, and SteriNet, and rock mass classification system, and the material I introduced to you yesterday and today. Okay? Do you have any question related to the examination next week? 下个礼拜四考试嘛，对不对？是不是？没错嘛，哈。So our examination will start from 8 o'clock. So you will have 2 hours to answer your question. Great. Whatever you want to have, you can bring it. Anything, 圆规啊、尺啊，你想到的你就带过来。对，但是不能带书啊，我们是 close book, is not open book. It will be close book.
画那个这些原子的话，我们是不是也要带一
扣题比较耐心。
我应该不会让你们做太复杂的立体投影的，所以应该不用带动名词，我不会给你一个题目叫你在那里直接画立体投影图，用那个纸去画，但是我可能 I could ask you to read the orientation of vector or plane from the staring net, right? I give you a staring net, right? And I ask you to read the orientation of the staring net, okay? Or I could give you, I could ask you to draw a plane or a vector on the staring net, roughly. You don't really need to have a transparent paper and to rotate. For example, I could ask you, please draw a plane which the stripe is north to the east 45 degrees and dip to the east-south direction 45 degrees. Please draw the plane roughly using a staring net. 我可能会叫你大概画一下，你画出来的结果我一看，我觉得说你差不多知道，你没有乱画，你就会得到分数。我们要叫你画得很精准，所以你不用带立体投影。如果要的话，我也会帮你们准备。If I give you the question related to the staring net analysis, then I will prepare the transparent paper and the staring net for you. OK? 好吧，还有没有什么问题？